All right. My name is Alex. Thank you for having me here. And today I'm going to tell you what is a WebAssembly component and why. These slides were primarily made by a colleague of mine named Luke Wagner, who gave a very similar talk about a year ago at this point. So first up, let's talk about what is WebAssembly and why. So this comes from webassembly.org, the official definition for WebAssembly, which is that it's a binary instruction format for a stack-based virtual machine. WASM is designed as a portable compilation target for programming languages. The operative phrase here being a compilation target. So for example, we have many programming languages today, and they all run on a wide variety of compilation targets. WebAssembly itself is a new compilation target within this ecosystem. WebAssembly can then be transferred to a browser or a WASM engine, which then internally runs it on these native targets through a compilation process. Some of the benefits of WebAssembly are its portability, its determinism, its control flow integrity, and its sub-process sandboxing. Some popular use cases for WebAssembly are, for example, taking a very large C and C++ codebase into a web browser. Some existing use cases for this are Unity, AutoCAD, Photoshop, Google Earth, and Figma. You can additionally run compute-intensive subtasks inside of a web browser. For example, codecs, compression, inference, encryption, and filters. There's a lot of usage of WebAssembly outside the web browser as well. So for example, as a plugin model, you can see this in CDNs, in databases, client apps, SaaS apps, Kubernetes, and streams. We also see this as an alternative distributed compute model in examples such as serverless computing or distributed actors, record and replay, and edge computing. But some of the questions that we ask ourselves as those developing a lot of this is, what can we do to grow WebAssembly even further from what it is doing today? So what big new use cases is WASM not quite great at, but is kind of posed to do a really good job at? So for this, I want to talk about 4 separate use cases that we want to see WebAssembly start doing much better in. So for example, the first use case, many compute platforms today are organized in such a way where you have some client-controlled app running on a platform-controlled interface. This platform provides a language runtime, which then additionally also has an SDK typically associated with it. The problem with this, though, is that this is quite a lot of work for the platform. They have to develop this entire SDK and choose a language. By choosing a single language, it means that the client is a much more limited sense. They can only use that one language for their app. They can't necessarily branch out and do what they want. So we can instead lean into WASM's language neutrality and linkable modules, and instead we can sort of shrink this. We can say the platform-controlled part of the system here is much smaller, and the client gets to control much more. They write their app as a WebAssembly module, and they get to choose their own language toolchain to then use internally. A language runtime probably has its own WebAssembly module, precompiled code associated with it, and this in turn could be shared on a registry, for example, which then allows code deduplication and code sharing across various applications. The language toolchain itself will come with a bindings generator that reads the platform interface and then generates this SDK. This in turn is another WebAssembly module, and these can all be linked together. This is very similar to OpenAPI or gRPC, but the key part is there's no network stack involved here. All of this is fast local function calls, which we'll kind of see throughout this talk. The benefits of this approach are that the client gets to choose the language, the host does far less work because they don't have to write their own SDK, and this helps emerging languages where you don't have to convince every platform to support you. So I'll call this use case SDKs for free. The second use case I want to talk about is, let's say you want to reuse code. Today we have many registries, but they're one per language, and it's very difficult to share code. They're kind of all siloed from each other. When you develop an application, you link in a number of libraries, but these all collide in the same address space, which means that a problem in one of these dependencies is going to be a problem for all of the dependencies at that point. Additionally, every dependency has equal access to all the capabilities of your application, such as secrets or file systems or the various services you have. This means that if one dependency is compromised, for example, and you pull that in, then it can get complete access to all of your secrets and your entire file system. You have no control or sandboxing between these dependencies. So we can instead lean into WASM's language neutrality and sandboxing support to imagine a single registry, which has a heterogeneous set of modules from many languages, This could in turn be backed by OCI for various cloud-native standards and cloud-native tooling support. And then we can develop our application a little differently by placing each of these WASM modules in a separate address namespace. This enables much finer-grained isolation where only the actual module that needs access to your secrets, for example, has access, and all the other modules do not have access. The benefits of this approach are we get to reuse code from any language, as it's all in the same registry. We can mitigate supply chain attacks because each module is independent of many others. And we can also help emerging languages where they don't have to rewrite all this functionality every time, but you can reuse components in the registry. I'll call this secure polyglot packages. So the third use case I want to talk about is, let's say you're designing an application, but you don't want to have everything all linked up into one giant big ball of mud. For this, you have two major options. One is you could use microservices. This is where you have one service talking to another over an HTTP stack. The problem with this is it's pretty complex. It involves a lot of networking, a lot of setup, a lot of orchestration, and there's a lot of overhead associated with this as well. You're going over the network. This is very beneficial if you want to scale each service independently, but let's say we don't actually need that scalability that microservices offer us. So instead, we could develop a modular monolith. This is where we could actually put all of our services into the same application, link these modules together, and we can get fast local function calls between here. The downside of this, though, is that typically this requires a single programming language, which means these two modules have to be the exact same language. Additionally, this is far less isolated with one another because now they're all in the same address space again, which has the same issues we saw before. So instead, we can lean into WebAssembly's language neutrality, sandboxing support, and linkable modules, and we can instead develop these two modules as entirely separate WASM applications and entirely separate address spaces. We get the same benefits of fast local function calls here, which means the major benefits, we get the memory isolation and the language choice, which are the major benefits of microservices, and we get this efficient cross-module calls, which is the major benefits of a modular monolith. So I'll call this use case modularity without microservices. The last use case I want to talk about is, let's say you have a bunch of teams and you want to factor out some code between them. So you've got 4 teams writing 4 services, they've got some shared authentication, some networking, and you want that to be owned by the platform engineering team. Today, if you want to do this, there's 2 primary ways. One is you could have an embedded shared library. You could put the shared library inside of each service, which then talks to the network, but it's very difficult to update this. It's very difficult to actually go through every single service and update that. Additionally, it requires per language effort to actually integrate this into each service. And then finally, it's a bit of a leakier abstraction too, because once you have a LinkedIn library, everything can all collide at that point. The other option here is a sidecar proxy, which I'm now realizing this is not exactly easy for you all to see, so I'm going to try moving over here. So in a sidecar proxy, the idea is you can have one service talking to another service, similar in the microservice architecture. This all goes over the network and goes out to the main network, but the main downside here is that this has significant overhead. This is the problem with the microservice architecture we saw before. So instead, what we can do is we can lean into WASM's sandbox support and linkable modules. We can imagine we have our teams writing their modules, our A, B, C, and D, and our platform engineering team, and they each write their logic as a WebAssembly module. The platform team, the actual teams are running against this internal developer platform so they can pass over their WebAssembly module, link them both together, and then run this on the actual infrastructure, which is a WASM engine. The interesting part here is the engine itself doesn't actually know that it's running these different modules. They're just all linked together and it's just WebAssembly. So the main benefits of this approach, we get this low overhead calls between modules, and we get this strong encapsulation between layers. It's kind of the best of both worlds of these 2 strategies over here. And this really starts to matter when we have multiple layers. So for example, let's take these teams and kind of shift them over to the side a little bit, and let's say that many teams are going to write in terms of a POSIX interface, not necessarily the internal developer platform. With this, though, we can typically use a virtual file system, kind of developed by the ecosystem or in the community, that implements POSIX in terms of, for example, a standard cache interface. We can then link these 2 modules together, pass it on down the line, and get some more modules, and again, run it on a WASM engine that is none the wiser and just running a bunch of WASM code. We can scale this a little bit further, and say that our engineering team might not want to run on their own platform. They might want to run on a platform as a service or a function as a service. And in this case, that platform might have their own high-level infrastructure or features written in their own WebAssembly module. As you can probably guess at this point, we can just link it all together into one giant module and run it on this WASM engine that is none the wiser. What this really showcases is that as the number of layers are growing here, this is where we really want that low cost and strong isolation. So this entire use case I'm going to call is virtual platform layering, this whole concept of virtualization. So the question now is, how do we support these use cases? And the idea in WASM is we're going to expand from a compile target, similar to native architectures, and instead build a new ecosystem, similar to, for example, containers or NPM or NICs. And the question then is, how do we actually do this? How do we make an ecosystem? There's a lot of possible answers for this, so I'm just going to go over a simple format. But the idea is, in the middle, we're going to have this standard distributable format. We'll have tools to build it, we'll have tools to deploy it, and we'll have tools to share and compose it. So for example, in the container ecosystem, this standard format in the middle is OCI. And then building, deploying, and sharing is a bunch of Docker and Kubernetes commands. And so you might be wondering, can we just use WebAssembly exactly as is today? So we put WebAssembly here as our standard format, as it is a standard format. We have existing WASM compilers that can generate WebAssembly modules from source code. But the problem starts breaking down pretty quickly after this. WASM really only supports shared memory linking today. So with two WASM modules, they go into the same address space. And this is specifically what we're trying to avoid for many of these previous use cases. So for example, this is very similar to operating system dynamic libraries, but that's not what we want. So instead, what we actually want are two WASM modules in two separate actual address spaces, and then some higher level orchestration is communicating values between these namespaces. Things like lists, things like resources such as sockets that are actually being transferred between these modules. So what we sort of want is an operating system executable of sorts. And so in the end, WASM itself, exactly as is today, is too low level and is not sufficient for this ecosystem. So then you might be wondering, well, what if we just use POSIX? Let's just put some POSIX around WASM and try and use that. The problem is that if we extend this, most applications end up being a couple of executables, a couple of files, maybe some directories, and this looks a lot like OCI. This is useful and this can be done, but the problem is that this doesn't solve the use cases we're initially trying to set out for. So these four original use cases are not very well solved with just WASM and POSIX. So what we've ended up deciding is we need something new for these use cases. So we want to reuse existing WASM compilers, and this is where components come in. So this brings us to the topic of this talk. What is a component? And the answer is an emerging, standard, portable, lightweight, finely sandboxed, cross-language compositional module. That is quite a mouthful, and so I'm going to dissect this word by word and give you some examples of how components achieve all of this. So for example, with modularity, we start out with a component which is defined by a set of imports, internal definitions, and a set of exports. All of your imports are functions, for example, that have various types associated with them, and this completely captures all I/O performed by the component, all implementation dependencies of your component. And this is in contrast to a fixed set of syscalls or runtime global namespace that you might be familiar with in POSIX. These internal definitions can be a series of functions and also core WebAssembly modules themselves. These in turn get to use all of the imports to implement associated functionality and have access to all of them. And then additionally, components are recursive, so a component itself could embed another component. All of these definitions and imports are then used to produce the exports of this component. Exports like imports are types, so this is a simple sort of rendering component, for example. And the idea is the exports capture how the outside world can interact with this component. This is in contrast to a fixed set of syscalls or a fixed signature, a main, which is more similar to the sort of POSIX style. One of the key aspects of components is that all interactions with the outside world go through imports and exports. There's no way to sort of reach into a component and tweak some of its memory, or it can't reach out from the middle. It has to go through imports and exports. This very strong property means that we can assign a type to this component. We can say that it has some imports, it has some exports. This is all described in an IDL we call WIT for the component model. And this is so common, we assign this a term of world, which describes the input and output of a component. A world itself is a contract between hosts and guests of what they can do. So we say, for example, that a guest component targets a world by implementing the exports and calling imports, and a host supports a world by implementing imports and calling all of the exports. Once we have these interfaces here, or we have these functions, we can group them together into what we call interfaces. So we can say we can import the file system, or we can export an HTTP server, which then groups all of these interfaces together. We can then take this one step further and standardize these interfaces. So we can call it WASI for WASI file system and the WASI HTTP handler. And the general idea here is that WASI's job is to standardize common interfaces between these many worlds that are possible in the component model. WASI does not simply have a single world, but instead there are multiple worlds that are possible in components, and WASI is simply sharing interfaces and defining this shared interface between them. So now I want to talk about the compositional nature of components. And to do this, I want to have an example. So we're going to start with this thumbnail program that was written 20 years ago and generates a thumbnail from a picture. Let's say we want to take that and turn it into an HTTP service, and then we also want to test that locally. So to start off, we're going to use some tooling called the WASI SDK to compile this to actually in a component. This component will then import the file system and then export a CLI interface. This is sort of like a POSIX executable of sorts. But we don't actually want this. We want to wrap this in another component which only exports a single function, which is the actual process of generating a thumbnail. This is working with streams, which are purely in memory, and this whole thing imports no memory, or no extra imports, sorry. So we do this with a tool in the Bytecode Alliance called WASI-Vert. This tool can then enable to polyfill a lot of this functionality. So for example, these streams are transferred to in-memory data structures, which are then used to satisfy the file system exports or imports as well. So all of this is one nice, cleanly wrapped up component that exports a single function. So the next thing we can do is we can publish this to a registry using a tool in the Bytecode Alliance called Whackage. Once we have it in the registry, now we can start writing our HTTP server that we want from this. So let's say we write our HTTP server in JavaScript. We can take this, run it through a Bytecode Alliance tool called componentize.js, and we can generate another component. This imports our thumbnail component and also imports perhaps a caching interface, and then exports an HTTP server interface. This is not suitable to deploy though, as we have these two components, so we'll use a Bytecode Alliance tool called Whack, which will then wrap all of this into a single component and link everything up internally. We can then say from earlier, this world targets this, or this component targets this world, which imports a cache and exports an HTTP handler. This is a very general world, which basically almost any host can support as long as it has access to these interfaces. But our problem is that we want to actually start testing this locally on our computer. So locally, we're going to have what more looks like a POSIX command or a CLI command with file systems and sockets and CLI. And so we're going to do one more composition. We're going to wrap all of this back up into one other giant component using some extra components on the registry. So for example, we'll use a file system cache, which can implement this key value cache interface in terms of the file system. And we can use this HTTP server component, which implements an HTTP server in terms of importing the thumbnail component and then implementing it in terms of sockets. And this all gives us a nice wrapping component, which then we can actually run locally. The really interesting part here is we've got two implementations of WASI file system. We got one here at the top, and we got one here in the middle. These are completely different. The one at the top is actually talking to the native file system, and the one in the middle is completely virtualized, talking to simply an in-memory data structure. And this is really showing off the benefit of this virtual platform layering that I was showing you earlier. So after all this, we've got this one nice giant component with lots and lots of components internally, and that's the sort of compositional nature of components. I want to talk now about the cross-language aspect of components. So let's say we have this world where we import a function, we import a log function and export a run function, and we want to target this from JavaScript. This looks very similar in terms of we can import a log function and we can export a run function. The key thing here is that the actual values we're dealing with in JavaScript are these high-level types. It's a list of strings. We can then run this through a Bytecode Alliance tool called componentize.js we saw earlier, and this generates a component that targets this world. We can do the same with Python. It looks a little bit different, as the idioms in Python are a little different than the idioms in JavaScript, But the idea remains the same. We can export a function, and we can import a function, export some types, and we get to work with native Python types like lists of strings. There's a bytecode alliance tool very similar to componentize.js called componentize.py, which generates the component. And then finally, we can do this with Rust as well. In Rust, this is modeled as traits for exports and generated modules for imports. And again, the types all use the native language types. And the tooling in this is a bytecode alliance project called Cargo Component. This is a lot of various tools here, but there's a very large amount of shared code, specifically with WIT bindgen and WASM tools, that assists in having this language bindings generation and various parsing of WIT and management of the types there. So WIT gives us all these value types, which are passed by copy. So for example, characters, numbers, strings, and lists. But WIT additionally has resource types, which are representing non-copyable resources. So for example, we could have a buffer on the host, or something like a socket. This has some constructors and some various methods associated with it. And then we can also export functions that refer to this type. When we implement this in JavaScript, we get to translate to all the native language idioms as well. So we can import a class from various WIT interfaces, and then the WIT constructor is mapped to the JavaScript constructor as well. The WIT method is mapped to JavaScript methods, and we can all use this in terms of return values as well. So this is showing you how you can not only import and work with various WIT constructs in many languages, you can also implement the same component in many languages. And this is can build on the compositional nature from before, where multiple languages can be talking to each other across components. So now I want to talk about the finely sandboxed nature of components. Let's start out by having two components here, each in their own separate address space. And we're going to say this top one imports an HTTP handler and exports what we're going to call a secret store. That's just some made-up interface over here where we're going to say it exposes a secret, where you can get a secret and then sort of read the internals of the secret. We'll then have this bottom component import that. It'll import our secret store and export a run function, and this will be linked up at runtime. So we're going to write this top function, or this top component in Rust, and we're going to say that we got these two traits. We're going to implement both the get and the expose function. And this bottom component is going to be written in JavaScript. This is going to import get, and then have some run details in various aspects. The sort of nitty-gritty here is not too important. So I'm going to run through an example of what a function call looks like when we call this component. So at some point, someone's going to call run, be that the host or another component. And what that is going to do, it's going to place this key in linear memory in JavaScript, let's say at address 4. That's going to get passed to get as we're transferring control over to the Rust component at this point. The runtime, the component runtime here, is going to copy this valued key from JavaScript memory to Rust linear memory, and let's say it ends up at address 8. This thing calls get in the Rust component at address 8, which then might go do some HTTP handling to kind of fetch the actual secret involved here. The result, let's say, is just XYZ placed at address 1, and then the next thing we're going to do is wrapping this up in a resource. So here, we're taking this address 1, putting it off on the side in a table, and what we get back is this handle 0. So we get this 0 to the Rust component, which is going to get returned, and this is represented as a table as part of the component runtime. The key part here is we are transferring ownership of this resource. So that 0 has been removed from the Rust component and passed down to JavaScript. JavaScript doesn't actually see this 1 because it can't actually see Rust's linear memory, but the component runtime knows where this all lives originally and can continue to access it. So JavaScript can then pass this back to Rust by calling expose, by passing in the handle 0, and Rust will end up having access to its linear memory as well. This is all very, very similar to inter-process communication, but this is all using fast local function calls. And again, this is all finely sandboxed and everyone's living in their own address space, and this is the nature of components. So next, I want to go over this lightweight nature of components. Components are very similar to core WASM as you might execute them today. So for example, you have a WebAssembly module, and you upload this to an execution platform. This execution platform might be organized into an ahead-of-time runtime and ahead-of-time aspect and a runtime aspect. This is very similar in a server context to the control plane and the data plane, for example. This WebAssembly module is compiled to native code, and then this native code is uploaded to the entire runtime fleet. That in turn has a WebAssembly runtime, which is then creating many instances that all refer to the exact same copy of the machine code, helping to deduplicate a lot of the shared resources here. And this is overall how we can achieve this sub-process sandboxing in WebAssembly, along with microsecond instantiation, for example, in runtimes like WASM time. So components have a very similar path along this trajectory. Components have this kind of compositional nature down here, which has many WebAssembly modules all baked in together. But when we pass it into our ahead of time aspect, we can actually sort of fuse everything together using multi-memory. This ends up producing basically one WASM module, which looks exactly the same as before. We can pass it to the compile step, we can blast that out to the fleet, and the only difference is we might have two linear memories over here on the instance as opposed to one before. And so overall, there's not really a big change with components. We're kind of all running the same aspect, and this is really showing off how there's no big component runtime associated here. It's all just sort of similar to the core WASM architecture. So let's say this component might actually be using modules from a registry. What this execution platform can do is also have a registry of compiled code for all of these modules on the registry. We can then say, instead of fusing these components together, we can actually reuse parts of this. We can have some code which is generated for this component, but we can also share all the pre-compiled stuff from the registry itself. When this is deployed to the fleet, which is a much smaller deployment artifact, this can all get linked up at runtime in a very similar manner as to before, and this is all run the exact same way with one instance or many instances referring to the exact same linked machine code. This is sort of DLL-like code sharing between various components. This is all the sort of lightweight nature of how components are very similar to core WebAssembly in that regard. The last thing I want to talk about here is the standard and portable nature of components. This is where the component model is layered on top of the WebAssembly core specification. The core WebAssembly specification has a formal spec, a reference interpreter, and a test suite, and we're working on the same things for the component model. If we take a look at this from the perspective of web browsers, the core WebAssembly specification is implemented in web browsers today, but not components. So the WebAssembly core JavaScript API is how you interact with WASM on the web. And the idea is we will also be creating a component model JavaScript API, which extends the WASM core API. Today, this is all done through a tool in the Bytecode Alliance called JCO Transpile. This is used to polyfill and decompile a component into its core WASM modules and some glue JavaScript code, and that's how we can get components running on the web today. We then see that WASI, for example, is defined in terms of the component model, and then JCO has support for this as well in terms of polyfilling this and implementing this in terms of web APIs. So this is sort of showing we're not quite to the point where the component model is a standard yet, but this is the trajectory that we're going on and how you can actually run this today in web browsers right now. So overall, this very loaded sentence is what a component is. So I want to talk a little bit about what components are today and kind of where they're at. So earlier this year in January, we released a developer preview called WASI P2. This primarily covered the component model and a subset of WASI interfaces. The major goal of this was stability and backwards compatibility to be a solid base to build on going forward. So for example, we provided an automatic conversion from the older version of WASI P1 to the new. And we're also committing to be able to convert WASI P2 to whatever comes next. Some of the main features of WASI P2 are, for example, the first wave of language support. This is, for example, Rust, JavaScript, Python, Go, and C. Some WASI proposals, such as file systems, sockets, CLI, and HTTP, and various others. We have this browser and node polyfill through JCO Transpile. We have the virtualization tooling through WASI-Virt, and we have this composition tooling through WAC, sort of everything we saw previously in these slides. And then finally, the registry aspect of actually publishing all this is a little more on the experimental side at this point, but is in development through this tool called Whackage in the Bytecode Alliance. And to give you a bit of an idea of what components are going to do tomorrow, the main thing we're going to be focusing on is concurrency. This is where in WASI P2, we do enable concurrency, such as await and async, but it's not really that great. It has a lot of downsides to it. Async interfaces are difficult to write in WIT. They require a lot of manual glue code in various languages, and they don't currently have the best performance. This involves a little bit too much copying that we would like. And then finally, the concurrency is not composable, meaning if you've got two components doing concurrent things, one of them is actually going to block the other, which is not the desired semantics you want. Additionally, if you virtualize any interfaces today that use async, you end up having to virtualize the entire world, which sort of defeats the purpose of virtualization or makes it so difficult it just basically effectively cannot be done. So the main goal of WASI-P3 is to be adding these future and stream types to WIT and components. The goal here is to be able to enable ergonomic and automatic bindings for many languages. So it makes this much easier to write WIT and much easier to integrate into languages. On the performance aspect, the idea is to have an IOU ring style ABI to make it much more efficient in terms of communicating all this data across components. And then finally, we're trying to solve this composable concurrency aspect specifically by adding in these built-in types for futures and streams. So one example of this is that today we have two interfaces for handling HTTP, one for incoming requests and one for outgoing requests. This is kind of a little weird and is a result of the fact of all the limitations we have today. So in the transition from WASI-P2 to WASI-P3, we're actually going to be able to have a single interface, which is just a WASI HTTP handler. So for example, if we have a service that both imports and exports a handler, and we have another service that both imports and exports a handler, we can link these directly together as opposed to having an adapter in between them. And this can all have the nice, fancy, fast, local async function calls that we're looking for in the component model. So that's what I have for today. This is sort of where a component is an emerging, standard, portable, lightweight, finely sandboxed, cross-language compositional module, and sort of everything that very loaded sentence might entail. These four main use cases we're trying to solve with what are our major use cases for the component model are these SDKs for free, these secure polyglot packages, this modularity without microservices, and virtual platform layering. WASI-P2 is ready to go today in terms of testing if you'd like to use it across various languages and ecosystems. And there's some various resources here if you'd like to get involved. We're always looking for more contributors, for more users to help work on the component model. So we have chats and meetings and various things like that. That's all I have. Thank you so much.